All right, so let's finish out this 9.1. A couple of more details that we want to look at. So, what happens if we've got some kind of distribution going on? Well, this is no different, even though that it's got some roots. It's got a root being distributed to both of the pieces. So we know that we actually have to multiply it by both of these. But it wouldn't be any different had we decided that it was x for the root 3. So then we would say, okay, well, I'm going to distribute this, and this is more used to it. We would say, like, okay, x times x, well, that would give me x squared, and x times 5 would give me 5x. That's the idea you want to follow for distributing a root. In this case, a root 3. So let's do it. It'll be root 3 times root 3. That means we get root 3 times root 3. For the moment, I'll write it as two separate roots. Then we have a plus sign, and then it is root 3 times 5. Now, the whole number is usually written in front of the root symbol itself. So you could write it as root 3 times 5, but you will more often want to write it 5 root 3, like that, because this automatically means that they're multiplied together. This right here, sometimes if people drag out their root symbols a little longer, then you're like, well, is the 5 under there or not? I can't really tell. So we don't like to do that. That's why we tend to put the whole number followed by the root symbol. Just as we would do that with when we had x times x plus 5, we wrote it as x squared plus 5x. We wrote the whole number in front of the variable. So now we have this root 3 times root 3. What do we do there? Well, think back to those examples we did on the previous video, where if you've got two roots that have the same index number, in this case it's not written, so they're both a 2, so these are both square root symbols, that you could combine them under a single root. So that's what we want to do here. We're going to say that this is root 3 times 3. Now you can go two different ways. You could combine the 3's together and make 9, and then ask for what's the square root of 9. Or you can write it as root 3 squared, then plus this 5 root 3. Then at this point, you're like, okay, well, this index is not written, so it is automatically a 2 for the index, and I have an exponent of 2. Let me write the index for a moment just to kind of help us out. We've got an index of 2 and a exponent of 2, which means they're going to undo each other, and I get the 3 coming to the outside. So I get 3 coming out. So really, in the end, I am with 3 plus 5 root 3. Now, can they combine together? No, they cannot. And an example of that was what was the previous video, where you kind of had two different actions of two different roots, and they could not combine in any way. So there, we will learn in a following video as to actually how you can combine when it's possible to do so. So your answer is either 3 plus 5 root 3, or you can write it the other way around as 5 root 3 plus 3, which might be the more standard way that you will see it. That was terrible. Let me just erase that thing and write it again. You might more likely see it this way. But they're equivalents, and you might think of this as just 3 plus 7 is the same as 7 plus 3. So in the end, just distribute. Let's try it again. This time we have an additional number, and then it's going to distribute. But that additional number, that whole number on the outside, will still follow through. It's still part of the whole thing that's multiplying. So when we distribute, we'll start here. It'll be 6 root 5 times root 6, and we'll write that 6 root 5 times root 6. Everything is multiplied together. even the 6 times the root 5. Then we also have 6 root 5 times root 8. So a plus symbol, and it'll be 6 root 5 times root 8. And again, there is a multiplication happening between the 6 and the root 5. Now, we just had an example again where a root times a root, you can combine it into one single thing. We have a root of a 5 times a root of a 6. So we will end up with 6 root 5 times 6. Then a plus sign, and we have 6, and then another single root of 5 times 8. Now at this point, we would actually do the multiplication. 6 root, now 5 times 6 is 30. And then here we have 6 root, well, 5 times 8 is 40. Now the only question you have remaining on this is, in order to follow our rules from previously, it says you need to reduce the radicand, or the inside of the root, as much as possible without getting a decimal. So we have to actually figure out, does these reduce any further? Well, this 30 is pretty easy because it reduces to a 5 and a 6. And a 5 is a prime number, and a 6 only breaks into a 3 and a 2. And notice that 5, 3, and 2 are all prime numbers, and none of them are repeated. And you would need them to be repeated so that you could pull out a whole number. And since none of them are repeated, it won't go any further. And you could simply say, okay, I'm not sure what you said, Mr. Stewart. So here we go, factor tree, 3 times 10. 3 is a prime number. 10 breaks into 2 times 5. 2 is a prime number. 5 is a prime number. And I could rewrite the whole thing. 6 root 3 times 2 times 5. But is anything going to combine together? Remember, our index is a 2. It's not written. So I need to get things grouped together in 2s, or with an exponent that's squared. And none of them are repeated, so I can't group any of them. So again, this one is not going to break down any further. So instead, I will leave it as 6 root 30. But what about the 40? Does the 40 break into things? Well, let's try it. 40 breaks into 4 times 10. And 4 breaks into 2 and 2. And 10 breaks into 2 and 5. Okay, so now it's 6 and then a root symbol of, how many 2's do I have? 1, 2, 3, and then a 5. Okay, so 1, 2, 3, and then the 5. We said moments ago that our index was a 2. So that means I'm going to grab 2 of the 2's. So 6 root 30 doesn't change. And then my 2's are going to be squared. And then I have the other 2 I didn't use and the 5 that I didn't use. Oh, but hey, now my exponent matches the index, which means this base number gets to come to the outside, which I'll use green, I guess. And so that means I have 6 root 30, which didn't change, and then I have 6 times 2 I got to pull out, and then everything else I didn't get to pull out. So again, you have to check to make sure that after combining the roots from their distributing, can they break out to where you could pull another whole number to the outside? So our final answer becomes 6 root 30 plus, well, 2 times 6 is 12. And then a 2 and a 5, they multiply to make 10. And there is my final answer. It's ugly, but I can't go any further anyways. I just have to leave it. And if you're typing this on the computer, you would type it exactly as you see. Of course, you could write it the other way around. You could write 12 root 10, then plus 6 root 30. I will say that. Or 12 root 10 plus 6 root 30. That doesn't matter. It's still the same answer. So you still distribute, but then you still have to check to see if you can simplify. Now, we keep referring to these rules of simplest form. You got to reduce the inside piece as much as possible. You can't have a fraction on the inside of the root. But then there's this one: no radicals are in the denominator. Okay, we have yet to see an example of this. What do? Well, here we go. What do we do when the denominator has a root that does not reduce to a whole number? Okay, we had it up here where it was a square root of 64, but that reduced to a whole number of 8. What if it doesn't reduce to anything? Well, this is where the term rationalize the denominator comes in. It's a method for getting rid of the root on the denominator. And I might say this: you multiply by a funny version of 1. You multiply by a funny version of 1. Let me show you an example. I'm going to erase these. They're just in my way, so I'm just going to get rid of them. Notice that I have a root on the top, which, by the way, root 5, since 5 is a prime number, it's not going to reduce. And then I have another root on the bottom, this root 3n. Now, I want to adjust this because I feel like it's going to be a whole lot better if I just get rid of the, oops, I thought I picked on white. There we go. And that was also super fat. So I'm just going to get rid of this. Let's just pretend it was root 5 over root 3. Okay, I know that that's not what the original problem said, but let's just pretend it was root 5 over root 3. How do I get rid of this root 3 on the denominator? Well, we said we need to multiply by a funny version of 1. But you got to be clever about the funny version of 1. You want to multiply by something that would cause this root on the bottom to go away. And we kind of did this already right here, where if we took root 3 and we multiplied it by another root 3, we multiplied them together, we simplified, and we got an answer of a 3. And look, the root was gone. So that's kind of your clue here, is to get rid of the root, you got to multiply by something that's going to get rid of the root on the bottom. And in this case, it's simply put as multiply by whatever's already on the denominator. But you got to do it to the top and bottom. Anything over itself is 1. Root 3 over root 3 is 1. So it's a funny version of 1. But I was clever, because when I take root 3 and multiply it by root 3, I get this. I have root 5 times root 3 over root 3 times root 3. And we did this already, but we can combine them into one root. Root 5 times 3 is root 15. And root 3 times root 3 is the same as root 3 squared. Or in between step would be 3 times 3. Which you would say, oh, well, that's just 9. So I end up with root 15 over root 9. And you'd say, oh, well, the square root of 9 is 3. So final answer, root 15 over a whole number of 3. And look at that. I have no longer a root in the denominator. By the way, 15 will not reduce any further because 5 and 3 are both prime numbers, and they're not the same prime number. But how do I know if this is equivalent to what's up here? Well, I will type it in for you. Root 5 divided by root 3 gives me that answer. Now, our other answer that we got was root 15 divided by 3. Do I get the exact same number? Yes, I do. So in order to follow rule 3 of not having a root in the bottom, we need to multiply to get by something to get rid of the root. Now let me go back to the original problem that was here. And you will see it's not really any harder. I'm going to go back to the original problem. It was not just root 3, it was root 3n. So what do I multiply by? Again, your clue is to just multiply by what's already there when it is a single thing. When it's only one thing, you just multiply by what's there. But you got to do it to top and bottom. Now, this will combine into a root 5 times a root 3n over a root 3n times a root 3n. And when I combine those together, I get root 15n, because 3 times 5 is 15, and then a root 3 times 3 is 9, and an n times n is n squared. Now, we already did the square root of 9. Oops, we already did the square root of 9, and it was a 3. What about the square root of n squared? Well, remember, this is an index of 2, and my exponent matches that index, which means I get an n to the outside. So in the end, this is root 15n over, well, square root of 9 was 3, and n squared, square rooted, they undo each other, I get an n. So 3n on the bottom. There we go. Let's try it again. Root 7 over root 2x. Okay, we're going to follow that same pattern. We need to multiply by something to get rid of the root. So if I multiply by the same root that's already there to top and bottom, let's see what happens. That'll be root 7 times root 2x over root 2x times another root 2x. That gives us, well, 7 times 2 is 14, so root 14n over, well, I can write it this way, 2 squared, because 2 times 2 is 2 squared, or 4, either one, and x times x is x squared. Now, if we remember, this doesn't have it written. There's no index number written, so it's automatically a 2. And then, hey, my exponent matches my index, which means a 2 gets to come to the outside. And similarly, the exponent of the x is a 2, and the index is a 2. So they undo each other, and that means I get a single x to the outside. So in the end, I get root 14n over, well, we said we pulled out a 2, and we pulled out an x. By the way, 14 will not reduce any further, because when you factor tree 14, it turns into 7 and 2, which are both prime number, and they're not the same prime number. One more time. Maybe I should have led with this example. I kind of did, but here we go. This time it's a whole number on top. There's no root on the top, but there is a root on the bottom. Okay, I need to get rid of the root. I need to rationalize the denominator. That's the word, rationalize the denominator. So I'm going to multiply by, since it's only one thing down there, I can multiply by that one single thing. If there's more than one thing, if there's a plus or minus with this, like on the outside, if it happened to be 5 over root 8 plus 3, we cannot just multiply by root 8. It will not be enough, okay? So I will show you an example of this kind of a situation in a moment. But for now, let's keep going. Since this is not in a root, I simply end up with 5 times root 8. The bottom becomes root 8 times root 8. 5 times root 8 is just 5 root 8. And root 8 times root 8 is the same as root 8 times 8, which we know is the same as 64. Or you could write 8 squared, either one. I will put a down arrow. We could also write it as root 8 squared. You'll find you'll get the same answer here. We'd be like, okay, what's the square root of 64? Well, the square root of 64 is 8. And then down below, we'd be like, okay, well, 8 squared, what's the index number? It's not written, so it's a 2, which means this 2 and this 2 will cancel each other out, and I get to pull an 8 to the outside. So I still have 5 root 8, and now I pull an 8 out. Oh, it's the same answer. And they will not reduce, well, they will. Actually, they will reduce further. Where do they reduce further? Well, doesn't 8 factor tree out a little bit? Here we go. 8 factor trees into 4 times 2, which 4 breaks into 2 times 2, which means this whole thing, 5 root 8, can be written as 1, 2, 3. 1, 2, 3. And of course, there's an 8 on the bottom. Well, what's the index number? We just talked about it down here. It was a 2. So that means I want to grab 2 of these. And I want to make this 5 root 2 squared times 2. That means that this is an index of 2. This exponent's of 2. I get this base, which also happens to be a number 2, to the outside. So I get 5 times 2. And then I didn't do anything with this one, so it's still there. And my 8 is still in the denominator, by the way. Now, I could multiply 5 times 2, or I can reduce 8 by 2. Let's just do that. That'll leave me with a 5 root 2 over an 8 divide by 2 divide by 2. That gives me a 4 on the bottom. And that's the final answer. So don't forget the other rules that we have learned, that if we can reduce a root, we still have to do it, along with trying to get them out of the denominator. All right, now, I said I would do an example of having a plus or minus additional something else. For example, here's this one. In fact, I actually want to start, well, that's fine, yeah. It's not just root 3 on the bottom. It's got this 2 minus root 3. These ones are a little bit more challenging, and I just simply want to show it to you. I'm not going to ask you to do it, but I want you to see it, because when you get to Algebra 2, you're going to be doing it a ton. But in between now and then, it's just good for you to see it. When you have more than just a single root or a single thing on the bottom, but you have a plus or minus symbol in between 2 items, you have to do what's called multiply by the conjugate. Oh boy, I hope that's spelled correctly. Conjugate. Which simply means this. We're going to multiply by, it's still a funny version of 1, but it's a very specific. Instead of 2 minus root 3, we will do 2 plus root 3. Basically the opposite symbol. And once, at first you're like, I'm not sure, why would you do that? But after we start to multiply the bottom together, we will see what happens. So I'm going to distribute the 7 just like we did on the previous problems. And that gives me 14 plus 7 root 3. But the bottom, we're going to have to do distributive property. 2 times 2 is 4. 2 times root 3 is 2 root 3. I'll switch colors here. I already used red. How about green, I guess? Negative 3 times root 2. Well, that'll be a negative 2 root 3. Remember we said we usually write the whole number in front of the root symbol. And then what about this? Negative root 3 times positive root 3. That would give us a negative root 3 times root 3. Looks very atrocious. However, notice some details. Positive 2 root 3 minus 2 root 3. It's like $2 and some change minus that $2 an exact same number of change. They subtract each other out. So that means I still have 14 plus 7 root 3 over, well, I didn't do anything with the 4, so it's still here. But now what is this? Well, we've done that one several times. We still have a minus sign in front of it. Don't forget that. But what's root 3 times root 3? Isn't that root 3 squared, or also known as 9? Square root of 9? Which, what is the square root of 9? Or the square root of 3 squared, which is the same thing. Would it not be 3? Which becomes, well, 4 minus 3 is 1. And what is anything over 1? Well, it's just itself. So in the end, the final answer is 14 plus 7 root 3, which does not reduce any further. So is this the same as this? Well, let's see. 7 divided by 2 minus root 3. You get that number. Then what about 14 plus 7 root 3? You get that same number. So yes, it is equivalent. Again, I'm not asking you to do them when there's several things on the bottom. You should, though, be able to do it when there's only one thing on the bottom, because that's pretty straightforward. This, you got to multiply by the conjugate. We'll do it one more time, then we'll be done. What do we need to multiply by? Well, what will be the conjugate? Well, it won't be root 3 plus 1. It'll be root 3 minus 1. Basically, you just need to do the opposite of whatever the symbol is between them. And think of these as parentheses around them to help remind you that we are multiplying. To help remind you also that you need to then distribute. So this becomes 4 root 3 minus 1 for the top. And then let's see here. Root 3 times root 3. I hope that you're getting better at this root 3 times root 3. Then root 3 times a negative 1. So it would be a negative root 3 or a negative 1 root 3. And then a different color. There we go. 1 times root 3, which is a positive 1 root 3. And then a 1 times negative 1, which is a negative 1. Root 3 times root 3, that's the same as the square root of 9, or root 9, which would be simply a 3. The middle two terms, negative root 3 and positive root 3, they're going to go away. They subtract each other out. And then we just have minus 1. So minus 1. And now you simplify. You'd be like, okay, here we go. What if we got 4 root 3 minus 1 over, well, what's 3 minus 1? 3 minus 1 is a 2. And I would leave it just like that. These were extra. These ones in the gray, they were extra. What you should be able to do, though, is like problem 17 and 15. All right. Thank you for watching.